This is a recast of the 4,200-word piece, Recurrent Neural Networks from Schnappat AI. This article discusses the history and applications of recurrent neural networks, RNNs, a type of deep learning technology used in machine learning. Let's listen in.
Artificial neural networks are a type of deep learning technology used in machine learning. RNNs, or recurrent neural networks, are a type of neural network architecture designed specifically to tackle sequential data. This type of data includes time series data, natural language processing, and handwriting recognition, among other tasks.
Yes, and the basic building block of an RNN is the recurrent neuron. This allows the network to store information and use it later in the sequence. Let's take a look at the history of neural networks and their evolution over time.
In the early days of neural network research, one of the biggest breakthroughs was the development of the perceptron, which was created by Marvin Minsky and Seymour.
After this, researchers began to explore ways to create deeper architectures with multiple layers to allow for more complex tasks. This led to the development of feed-forward neural networks, FFNs, which are designed to process data in a linear manner.
However, FFNs lacked the ability to process temporal or sequential data as they lacked a mechanism for storing information from previous inputs. To solve this problem, researchers developed recurrent neural networks, RNNs.
RNNs are able to process sequences of data by utilizing feedback loops that allow the output of a neuron from a previous time frame to be fed back into the network as input for the next time step. This feature makes RNNs very well suited for tasks that require understanding of both current and past information, such as language translation and speech recognition.
RNNs also have the ability to process variable length inputs and maintain a state within the network that has an impact on the processing of future inputs. This makes them ideal for modeling time series data. The architecture of an RNN consists of three primary layers: an input layer, a hidden layer, and an output layer, and can contain multiple hidden layers depending on the complexity of the task.
RNNs are a powerful tool in machine learning as they have revolutionized tasks such as language processing, speech recognition, and time series forecasting. As a result, they are being used increasingly in many different fields. For instance, they are used in medical diagnostics for disease detection and pattern recognition, as well as in autonomous vehicles for navigation and object detection.
Now let's talk about one type of RNN in particular, the long short-term memory model. This was introduced in 1997, and it is designed to overcome the issue of the vanishing gradient problem that is common with traditional RNNs. LSTMs have become one of the most popular and widely used types of RNNs because of their superior performance in processing complex sequential data. They have been used in various applications such as machine translation, image and video captioning, language modeling, and recommendation systems.
Another popular RNN model is the gated recurrent unit model. Similarly to the LSTM model, this is designed to address the problem of vanishing gradients. It achieves this by introducing two gating mechanisms, a reset gate and an update gate. The GRU model has been found to perform well in a variety of natural language processing tasks, such as language modeling, machine translation, and sentiment analysis.
So what are some applications of RNNs?
Well, they can be used in speech recognition to recognize and transcribe speech. They can also be used in language modeling to predict the next word in a sentence. In machine translation, they can be used to translate text from one language to another. They can also be used for image captioning to generate descriptive sentences or captions for images. They have also been applied to time series prediction and anomaly detection by learning to identify unusual patterns in data.
And we can't forget about natural language processing, NLP. NLP involves the use of computer algorithms to analyze, interpret, and generate human language. With the help of RNNs, machines can understand natural human language by learning different patterns and structures inherent in it. RNNs are capable of recognizing contextual dependencies among words, allowing them to construct grammatically correct sentences. This technology has countless real-world applications such as virtual personal assistants, automated content generation, and text sentiment analysis.
Finally, we have speech recognition, which is a key application area for RNNs. Automated speech recognition, ASR, is a technology that transcribes spoken language into text, and this has become increasingly popular due to the rise of digital assistants like Siri and Alexa. RNNs have improved the accuracy of AESR systems by using long short-term memory, LSTM, cells to store information over time. With these advancements, the potential of NLP holds dynamic possibilities for revolutionizing communication methods and transforming industries worldwide. Another application of RNNs is image captioning. This involves taking an image as input and generating a textual description for it. An RNN is used in the second phase of the process to generate sentences in order to accurately describe the image. This can be a significant help for individuals who are visually impaired.
Moving on to time series analysis and prediction, a time series is a set of data points collected over time. Examples of this data could include stock prices, weather patterns, or website traffic. RNNs can be used to analyze and predict future values in these data sets using patterns from the past. This can be critically important for financial decisions and weather forecasting.
Despite the potential of RNNs, there are some challenges that need to be addressed before they can be fully realized. The vanishing and exploding gradients problem is one of the major challenges for RNNs. This is when the gradients become too small or too large when propagated back through time. As the gradients become too small, the network is unable to learn effectively, while if they become too large, the model can't converge. Additionally, overfitting is a common problem in machine learning with RNNs. Overfitting occurs when a model becomes too complex and starts to fit the training data too closely, resulting in poor performance on new data.
Fortunately, there are various techniques that can help address these issues. Gradient clipping, weight normalization, and pre-trained parameters can be used to mitigate the vanishing gradient problem. Regularization, early stopping, and dropout can also be used to prevent overfitting in RNNs.
Aside from the theoretical challenges, there are also computational challenges associated with RNNs. Training these models requires a lot of computational power and memory capacity, and can be difficult to implement on low-end hardware. To address these challenges, specialized hardware such as GPUs and custom chips can be used, as well as parallel computing and model compression techniques.
In addition to the existing approaches, there is also research into hybrid models combining RNNs with other neural networks. This combination offers the ability to perform better on a wider range of problems and provides a more efficient training process. Attention mechanisms have also become a standard component in many modern sequence-to-sequence models, as they allow the networks to selectively attend to relevant parts of the input sequence.
Lastly, there have also been advancements in optimization methods for RNNs. Backpropagation through time is a popular optimization algorithm, while LSTMs are a special type of RNN that have been designed to address the vanishing gradient problem. Other optimization methods include adaptive learning rate methods such as ADAM and ADAGRAD and dropout regularization.